Hello everybody, by the end of this video you should be able to identify the 7 base units and a whole bunch of metric prefixes, and you should be able to describe reasons why the metric system is really much better than other systems of measure that we use, like the one that we use in the United States, the English system of measure. So this is going to be titled the metric system, and we're just going to go over some of the basics. So realize that the metric system is kind of an old name for the system that you guys are all used to. The current name is the International System of Units, which we abbreviate SI. It comes from the French Système International des Unités, and so that's Système International SI. And so in the SI, there are 7 base units, which are flying onto your screen right now. And you'll see that there's the kilogram, the meter, the second, the Kelvin, the mole, the ampere, and the candela. Those are the 7 base units, and I would memorize them however you need to do it. Pause the video, stop and rewind, however you want to do it. Okay, those 7 base units are the units that every other unit in science is based upon. We can rewrite every other unit that's not one of those 7 in some way by using base units. So the good thing is that 2 of these we are not going to use in the class, but I still think it's important for you to know all 7 of them. But we're just not going to use the last 2, the candela and the ampere, in class when we do sample problems. So I think it's important, before we get into some of the other more technical stuff, to talk a little bit about the history of some of these units. So let's talk about the kilogram first. The kilogram is really interesting. Actually, if you really wanted to, you could read about some of this, but the kilogram is really the only base unit that is left that is based on an artifact. It's a thing. See this thing right here in the middle? That thing, that is called the International Prototype Kilogram, and that's what a kilogram weighs. And so if people talk about this all the time, if a ninja were to come in and cut that in half, then the kilogram would be half of what it used to be. Okay, but that doesn't happen. They have different copies of these all over the world, and they calibrate them every so often, once a year, maybe more often. We have one in the United States that's a copy of the original, so it's kind of interesting. So, but historically speaking, back in the Dark Ages, they would say that a kilogram was the how much 1 liter of water was, how much mass was in a liter of water. So that's kind of interesting. It's kind of based on something that we know, and it's the only base unit that does use a prefix. You can see this. It's not the gram. Okay, you'll see this on questions coming up. It's not the gram, but it's the kilogram or the kilogram. Okay, so then next we're going to have a meter. I'm sure that everybody that I'm speaking to knows what a meter is, and much like the kilogram, this also used to be based on a thing. There was an IPM, an International Prototype Meter, and this is a copy of that. That's a picture of what the IPM looked like, and classically we defined it as 1/10,000,000th the distance from the equator to the North Pole. And that was kind of interesting because we were using the Earth to do that. The thing about using objects to define a base unit is objects can change. Much like my silly example of the ninja with the kilogram, you know, this meter, the IPM could change, or the distance from the North Pole and the equator can change. It does change, actually. The Earth is not a static spherical shape. It actually kind of kind of goes in and out a little bit at its poles, so it's kind of funny. So what we need to do is define it by something that is never going to change. And so we define the meter now as some fraction, and you see the fraction right there, of how fast light travels, or how far light travels in 1 second. And so the speed of light is not going to change. So there it is. So let's talk about the second for a little bit. Christian Huygens was actually developed one of the very first clocks. He called it a chronograph. Chrono meaning time, graph meaning to write down. And the second is a classic unit that actually is not based on powers of 10, which makes it difficult when we want to do conversions, because I'm sure in the past you've done conversions that are like, hey, 60 seconds in a minute, 60 minutes in an hour. It makes it really hard, or harder, I should say, to do some of those conversions. And again, it was defined as some part of a day, some fraction of a day. But again, the length of the day changes as the Earth moves around the sun or spins on its axis. So they use something that doesn't change, and that's how some sort of electron moves in a cesium atom. And that's where we get the idea of an atomic clock, one that is not based on the motion of the Earth or the motion of the Earth around the sun, but one that is based on how atoms move, that's not going to change from day to day, hour to hour, year to year. And so that's pretty neat. So the next unit that we should talk about is the Kelvin. The Kelvin is very close to the Celsius scale. The thing about it is, in order to understand Kelvin, you should understand what temperature is. Temperature is how fast molecules, particles move. Okay, so particles, the faster they move, the higher the temperature. And so Kelvin has no negative numbers. It has no negative numbers because if we think about temperature in terms of molecules moving or particles moving or atoms moving, whatever you want to say, then what you'll notice is that a negative value for temperature doesn't make sense, because once you get down to zero, zero should mean that there is no motion of the particles. So it's kind of an interesting thing. So Celsius was based on the freezing point and boiling point of water, 0 and 100 degrees. But the Kelvin temperature scale is based really on the Celsius scale, but what we call absolute zero, the point at which all molecular motion stops. Molecules don't move then. And the thing to keep in mind also when you say this is that you're talking about you're not talking about degrees Kelvin, you're only talking about Kelvin. So when you report a temperature in Kelvin, you're talking about 300 Kelvin. You don't say degrees Kelvin. Okay, and then the last of the base units that we're going to talk about is the mole. The mole is not a furry animal. I mean, it is a furry animal, but in chemistry class, it's not the furry animal. We're not going to talk about that. Okay, it's actually defined as the number of atoms in 12 grams of carbon-12, which is one single isotope of carbon. If those words bog you down, we'll have more later on what isotopes are and why it says carbon-12 and things like that. But it's an amount of substance. A mole is used exactly like a dozen is. So if you say you have a dozen books or a dozen ring stands or a dozen beakers or a dozen flowers, no matter what we're talking about, a dozen always means 12 of whatever we're talking about. So a mole, if we had a mole of atoms or a mole of molecules or a mole of people or a mole of pennies or a mole of chairs or a mole of whatever, a mole is always defined as 602 hexillion, 214 pentillion, 150 quadrillion things. It's a lot of things. It's such a big number that it doesn't make sense to talk about that many things, except when we're talking about very, very small things like atoms or molecules or electrons, protons, neutrons, or whatever, okay? Because it's just completely unreasonable to talk about if we had a mole of donuts, okay? Or a mole of moles even. That would be really kind of funny and disgusting, actually. I read an article about it. It would be weird. Maybe I'll post it for you to see. Anyways, so that's about the base units, okay? So that's a little background. But now we need to talk a little bit about derived units. And so derived units are any of the other units in the SI. Okay, so if it's not one of those 7, it's a derived unit. Okay, that's it. I mean, it's really that simple. If you know the 7, then you know what all the derived units are, because if it's not one of the 7, it's a derived unit. And so what makes a derived unit derived? Well, if we think about one of the most common derived units, the liter. The liter is actually a measure of volume. So if we look at how we determine the volume of something, here's a cube, okay? And cube has a length and a width and a height, and we can measure those in the unit of length. The base unit for length is meters. So a length is measured in meters, a width is measured in meters, and a height is measured in meters. And so we know that the formula for volume is length times width times height. So what we're doing is we're doing volume times equals meters times meters times meters, and it becomes cubic meters is what the volume is. So it turns out that you can write a liter as some value of a cubic meter, and so that's why it's derived, is because a liter can be defined as some base unit, okay, some multiple of a base unit, and in this case it happens to be a cubic meter. A more common example of a volume measurement is a cubic centimeter, or a cc. Maybe you've seen it on TV, like a TV show with doctors, a ER, or some sort of or house, where they ask about, get me 5 cc's of whatever pharmaceutical, stat, which means hurry, on immediately. And so, but 5 cc's, that's cubic centimeter. And so they're saying that centimeter, it's not a milliliter. They're using the base unit form of the volume. So it's kind of interesting that stuff can happen. A couple other things, and I'll go quickly through this, so don't necessarily worry about these specific things, but something that you'll see is a newton. A newton, it's not on the list of 7 things, so it must be derived. It's derived because it can be rewritten on the bottom. You can see a newton is a kilogram meter per second squared. Hey, good. Okay, so notice kilogram, meter, and second are all base units. And we can do this with a joule. A joule is a unit of energy. You're going to hear about joules later on in the year. And so, again, you can rewrite a joule as a newton meter, but we know that a newton can be defined by base units. So a joule is actually a kilogram meter squared per second squared. And so the base units are used to rewrite these derived units. Any derived unit you can take and rewrite it using base units. Why do we have derived units? It's because it's way easier to say joule instead of a kilogram meter squared per second squared. It's just easier, and they honor really important scientists with naming of the units. Sir Isaac Newton is the Newton. Joule, who did a lot of work with energy. Even Kelvin, Lord Kelvin, has a base unit named after him. So there's a lot of things behind these units. But in the end, if it's not on the list of 7 base units, it's a derived unit. Okay. As we move along, one of the biggest beauties of the SI system is that we can use prefixes to represent large and small numbers. And so there's a list of prefixes on page 26 of your notebook, or not of your notebook, but of your textbook, the Coates and Treichel textbook. And again, I would try to make sure that you memorize these. And there can be prefixes for really big numbers, and the ones flying in now are prefixes for really small numbers. And so if you have a number that is really big, billions and billions, okay, instead of saying, 15 billion meters, you could say 15 gigameters, and that makes a little more sense. They've done some studies, and they've figured out that humans can only understand numbers up to about 100,000. When you have more than 100,000-ish, then numbers, if you see that many things, the mind is hard to understand how many things it is. So just to give you an idea, 100,000 people would be the Lincoln Financial Field full of fans, okay? And so at a sold-out Eagles game, there's about 100,000 people. It's a little less, but, that's 100,000. Anything more than that, our brain can't process it as well. I would definitely write these down. You can either write them down here, or you can write them down in the from the textbook. And I do want to point out this here. Yes, that's not a typo. Okay, that is its symbol. That symbol there for micro is pronounced mu. It's a Greek letter. It's a lowercase Greek letter, mu. Because if we look, capital M is being used, and then lowercase m is being used. So we need a different M here for micro, so they use that. And it's kind of like a U with a tail on it, I guess. But that's what it looks like. I'm pretty understanding when you write micro. And yeah, you're going to need to know, probably the important thing to know is the symbols and also their powers, what they mean. Like deci means 1/10 or 10 to the minus 1. When we get into conversions, those are going to be important. Okay, so take a minute again, pause the video, or or go look it up in the book or whatever in order to write these down. Okay, now again, how does this help us? Let's do some examples. The distance from the Earth to the sun. If you take astronomy, that's one of my things. It's about 150. Let's see here, billion meters. Okay, 150 billion meters. So instead of saying 150 billion meters, a number so big that we don't understand what 150 billion of something is, okay, let's rewrite it. Let's write it as 150 gigameters. Gigameters, 150 is something that we can easily understand. 150 is one of the grade levels at Collingswood High School. There's about 150 people, 200 people per grade level. So that's a number we can kind of understand. So that's why we use prefixes. Okay, and so the distance from New York to Los Angeles is about 5 million meters. 5 million meters can definitely be rewritten as 5,000 kilometers, or even 5 megameters. I think that, we understand what 5 is, okay? We understand what 5,000 is. And so it becomes a little bit easier for us to comprehend in our head what this is, okay? And so now we go the other way. If we talk about a mass of a grain of sand, that's going to be something very small. So that's 0.00067 grams. That's a tiny, tiny number, okay? And so we can rewrite that as, instead of 0.00067 grams, as 670 micrograms. So there's that micro for you, okay? And 670 is a number that our brains can kind of comprehend. Maybe not combined with microgram, but the idea of manipulating 670 using math sense and using what we learned in math probably is a little bit easier to do. So that's what we get. So that's your introduction to the metric system, and good luck, and we'll use this again.